halfway to spring break. I do the happy dance. That's why. We're getting close. We just finished lab on Monday, and we were talking about components that interact with their environment. We've been speaking systems speak all semester. Gosh, have we only known each other for 3.5 weeks? It seems like a lifetime. And this class keeps on dragging me. We started out talking about the balloons and the straws, and then we specifically started talking about the push, the flow, and the resistance. V equals IR. And we said electronic systems can be discussed. What is this? I don't know where this pen came from. This is sort of goofy. V equals IR. And we said when we're talking about electronics, we can use those symbols, the push, the flow, and the resistance to describe and characterize what actually happens when we turn it on. Okay, so when we allow energy to flow through the system, we can characterize the push is this value at this point in the circuit or the system. The push is this point in this part of the circuit, and then this is the resistance, so we'd be able to measure all these things. We've started talking about real wires, real batteries, and real resistors. Okay? Real wires carry current. Real batteries provide push, and real resistors provide, wait for it, resistance. Okay, so the resistors are pretty, they're giveaway. They're working very well. But we have real versions of what we're talking about there. In a real quick review, as time stopped, I'm waiting for it to go 12 minutes. Look at the second hand. Oh my gosh, it's never going to be halfway this morning. Oh,
No, it just stopped too.
Did it just stop?
Yeah.
Okay, mine's still going, so we can go, right? It's not some Twilight Zone episode. We're stuck in physics, I hate it. We know that this little guy provides resistance, and we've already seen the secret system, the secret handshake, the secret code to read that value. And only because we've been using with it, and I know what I stuck in there, brown, black, red happens to be 1,000 ohms. It's a very common number to start with, so 1,000 ohms. And we know that if we were to provide power to that guy, we could make a circuit. So we usually have something that looks like a positive, and then we have the resistor, and then we have something that looks like the negative, and then we wire it up. Okay? And typically, inside the hieroglyphics for circuits, that's what a battery looks like. That's sort of the international symbol for a battery. It has a long line, that's considered the positive. It has a short line, that's considered the negative. And I guess if you really think about it, it sort of looks like a battery. There's negative, that's why that's short. There's positive, that's that guy. It doesn't need to be a circle. It's just sort of how we write that. It could very easily be exactly what we have inside the lab. If you recall, the screen's up. Over here is positive, and over here is G and D, and over here is negative, and we literally have wires that connect the positive and the ground. Okay? Negative is what we call a battery terminal, but for our system up there, it just means that if we had another terminal down here, this would just be, that's negative of that guy. It just means below. So positive means above the ground. Ground is what I give away, it's ground, and negative is below the ground. So we've seen the circuit. And we know how to work with voltage equals current times resistance. And if this is the circuit, we could probably put some letters on here. The total voltage equals the total current times the total resistance. Okay? That's all we're talking about, right? There's only one push, so that's the total push. There's only one flow of current, and this thing just continues. It's sort of, my finger is making a circle, which is why we often draw it in a circle. You can put it clockwise, counterclockwise, laying on a table, however you want to put it. And then the resistance total is just that guy. Okay? We then, quick review, said, oh, fantastic. What if you change the circuit and put two resistors one after each other? Okay? Oh, by the way, we know how to use that breadboard now. We know how to connect things. We said if you change the number of resistors, and you place them such that the current goes through one, then the other, those things are in series. Just like the World Series, you play the World Series games one after the other. You typically don't play Game 3 before you play Game 1, and you typically don't play Game 3 at the same time you're playing Game 1. That's not how it works. Basketball is a different story because you have different teams playing different seeds. But in series, one after the other. So now we have this idea of voltage total equals current total times resistance total. But our resistance total is not simply just one resistor, it's two. So our system has gotten more complex. Our total now has to be calculated. We have extra resistors. Again, it's a real quick review. Series circuit, R total, two resistors, pop quiz. How do we calculate the total resistance when we put resistors one after the other? I'm sorry? We add them together. So yeah, if we were to label these guys, resistor 1 and resistor 2, you can call them whatever you'd like. Resistor 1 plus resistor 2, they simply just add. They don't multiply. Some people might think that adding an extra step might complicate the system by making it, multiplying it. Some people will say it even makes it more complicated by exponentially worse. In this case, it makes it just this much worse. You just add an extra step. So we keep on generalizing this circuit to real life situations. If you need to go get your driver's license and there's only one counter, then you go to the counter takes 10 minutes, and that's the resistance to your time, and then you're out. But oh, by the way, now there's a new thing where you have to go ahead and get certified or whatever, and so this is a 10-minute counter, and that's also a 10-minute counter, but you can't go to the second counter before you get your stamp from the first counter. Oh, you've just turned it into a 20-minute visit, because they add linearly. So there's examples in real life, just like there's examples inside electronics. Very, very simple. We just add them up. Once we add them up, and I believe they're both, looking at the colors, brown, black, red, brown, black, red. Okay, good morning, sir. They're both 1,000 ohms. Okay. Now that we have 2,000 ohms, this value of the circuit and this value of the circuit are obviously different. If we have the same push, if this guy gives us a certain amount of current, if we have the same push, let's go ahead and put some values in here. I love 10 volts, only because 10 volts isn't easy for me to calculate, and we can adjust it. We could use a 9-volt battery, we could use a 1.5-volt battery, I like 10 volts. If we want to calculate the current, V tot, I'm just rewriting it, is the current times the resistance. I want to calculate the current, I have to divide both sides by R tot. I get V tot over R tot equals I tot. That sure looks like my total voltage, which is 10 volts, over my resistance total, which is 1,000 ohms. And we get a value, we've done it before, right? It was 0.01 amps. Does anybody have a calculator? Did somebody do that for me? I'm sorry, I said 10 was an easy number to divide by, and then I just proved it because I can't divide by it. 10 divided by 1,000. 0.01. Look at that. In the lottery. 0.01 amps. Over here, same situation. V tot equals I tot times R tot. I want to find the current. What is the flow? How fast will electrons get to the system? How fast will the positive current get to the system? I tot equals V tot over R tot. I'm just using the tot thing. Because I'm using R tot, I don't use the value of R1 or the value of R2. I use and. I use 1 and 2 because they add up. I get 2,000. 10 volts over 2,000 ohms. If I go ahead and do that, did I do that right? Is that point? Oh, What's so special about 0.01 amps and 0.005 amps? Again, I'm looking for the relationship. If I change this to milliamps, this is 5 milliamps, and this is 10 milliamps. What's the special relationship between 5 milliamps and 10 milliamps? 1, you represent with a 1 and a 0, and the other one. What's the relationship between 10 milliamps and 5 milliamps?
5 is half.
Thank you. Okay. 5 is half. What does that mean systems-wise? It means that the flow has gone down by half. It's half as fast. It's half fast. Right? Okay, it's half fast. This circuit is half fast as compared to this circuit. How did we slow things down by half? We added another resistor. We doubled the resistance. So it turns out there's sort of this, if you double it, it goes down by half. They're inversely proportional because of this stuff, okay? The i's on the numerator on this side of the equation, and the r is in the denominator on this side. You can get all mathy and say, yeah, it makes sense. You double the resistance, the flow goes down by half. It makes physical sense. It's true. We measure with our machine. The more resistance you add to a system, the slower the current. That's true in electronics, and it's also true, this guy, okay? It's also true in business. If you add an extra counter that you have to go through to get your license, you're going to slow things down. It's just the way it is. If you add an extra step in a standard procedure in the laboratory, well, let's add an extra step. I'm making cookies. Let's add an extra step. It's going to slow things down, which is how it is. It's obvious, but we want to make sure that we understand it because it's there. Okay? What happens if we add a third resistor? Oh my gosh, how difficult can it be? We add them all up. They're still in series. If I add them in series, we add them all up. They keep on going. So, of course, here's the next question. I need to re-erase this. Here's my ground and my positive, still using that. Here's my positive to these guys. Here's my ground to those guys. I grabbed another copy of a brown, black, red, brown, black, red. You can number them all you want. Let's just still call this guy R1. Let's still call this guy R2. There's still 1,000 ohm resistors. But you already know this answer. It's still a circuit, so the circuit is still V tote equals I tote times R tote. That's true. However, R tote is different this time. Okay? We added a second 1,000 ohm resistor, but this time, instead of adding it one after the other in series, we've added them in parallel. Why are they called parallel? Because, I don't know, from geometry, those are parallel lines. Okay? So if we were to draw this side to side, I'd see positive 10 volts, sort of like that, up and over. I'm just drawing it this way. You can draw it however you want. That guy, okay? These guys are in parallel. They can be parallel up and down, they can be parallel sideways, they can be parallel 45 degrees, they're parallel. This guy goes this way, here's R1, here's R2. You already know that there's a difference because we've talked about it. When we add resistors in parallel, we get a different equation. R total is not just add them up. Anybody recall offhand how we add them up now? How we calculate the total resistance, the total resistance. New system, they're in parallel. The over stuff. We still add them up, but I don't know how, I'm asking if I didn't memorize it because you always have your equations and you always have Google in front of you when we're taking our exams, but way I sort of remember it is R2 and R1 are over each other. That's sort of a mnemonic. Okay? So they add up because they're 1 over each other. The only difficulty here is if you look at it just practically, if I add them up as their inverses or their reciprocals, since this guy is, I don't know why I'm using red, ohms, and this guy is ohms, then when I'm finished, I get 1 over ohms. The units are wrong. So at the very end, I have to take the reciprocal of the answer and put the units back up. Okay? But I add them in reciprocal, I add the denominators, and then I bring it back up to the numerator. So that sort of looks like this. The R total, still the same circuit. V total equals I total plus R total equals 1 over 1,000 plus 1 over 1,000, and then when we're done, take the reciprocal and put it back where it was. If I have 3 resistors in parallel, 1 over 1,000 plus 1 over 1,000 plus 1 over 1,000. If they're not 1,000s, 1 over whatever the value is, you just stick it in, okay? 1 over 1,000 is a value, 1 over 1,000 is a value. I think I remember from school, common denominators, you don't need to do this from grade school, you can use your calculator. But 1 thousandths plus another 1 thousandths is 2 thousandths, because they have a common denominator. And you can simplify that. 2 divided by 1,000 is 1 over 500. And if you take the inverse of 1 over 500, you get 500. Okay? You can also just plug it into your calculator. 1 over 1,000 plus 1 over 1,000 gets a number. And then when you're done, you take the inverse of that, you get 500. Our total resistance is 500 ohms. It used to be, when we had these guys side by side, we went from 1,000 to 2,000. We doubled the resistance. Now we have 1,000 and 1,000 in parallel. It used to be R1 plus R2 equal 2,000. Again, looking for relationships. What's the relationship of 500? Well, maybe not even that. Let's do this. R1 is 1,000, and then we put another R2. It was 1,000. Let's look at it this way. What's the relationship between 500 ohms and the original resistance of any one of the resistors? Is done by half. We've got this double half again. Instead of adding a second resistor behind the first one, like we did over here, where we had 1,000 plus 1,000, because we added them behind, now we've added them in parallel. The answer when we get in parallel is that this is just me thinking goofy. It's not 1,000 divided by 1,000. But, oh, by the way, the real answer is 500. Went down by half. Okay? If that goes down by half, then for this circuit, V tote equals I tote times R tote. V tote is 10 volts. R tote is 500 ohms now, equals I tote. 10 over 500. What is it? 500. 0.02. 0.02 amps, which is 20 milliamps. Is that a surprise? Shocking. 1,000 ohm resistor. Where did I get 10M? When did I write that there?
10 minutes.
10 minutes, thank you. I was having a minute discussion. What a stupid spell. We're closer to spring break now than we were at the beginning of the class. Second hand is still not moved. Fantastic. I did say 10 minutes, didn't I? What a stupid explanation. It's a lovely way to think about it. Our 1,000 ohm resistor had a current of 10 milliamps. 2,000 ohms, one after, had a current of 5 milliamps. Two 1,000 ohm resistors in parallel has a current of 20 milliamps. Oh my gosh. If you add the same resistor after it in series, the current goes down by a half. If you add a second resistor in parallel, the current goes up by double. That half thing again, that 2 thing again. Okay? We've doubled the flow. We cut the flow in half when they were after each other, and then when we parallel them, we double the flow. And of course, I keep on using this example because my puny little brain can't get over it. If you're at Walmart and customers are going through lane 1, and there's a long lane of customers, and you want to speed things up, you don't add a second checkout and ask them to put their things back out onto the belt again. You open a second checkout, but you open a second checkout in parallel. And now you can get twice as many customers out. Okay? Now that exact half only works when you add an identical path. The resistors have the same value. As soon as you start changing the resistors' values, then you have to do the math to find out how they go up. Just adding another resistor, doesn't matter what value it is, that doesn't make sense. I mean, in reality, what if you add a checkout line at Walmart? If it's exactly just the same speed, you double the flow. But if this person is a new trainee and they're making a commercial and their boss is there and they're making a lot of mistakes and it takes like 20 times, that's not going to speed things. It will speed things up a little bit, but not as much as just adding the same thing again. And that's not just, you don't have to work through the math, you just calculate the math. Okay? Good. Then, this is the circuit we built last week. Oh, so complex. Look at that. And one of the things we love to do inside systems is we like to learn parts. Before the wiring lawyers get a hold of me, this has to go to that column, right? I changed the color of the wire. We like to look at individual parts, just like individual Lego parts, and then we snap them together. We build stuff. That's what builders do. That's actually what engineers do. Engineers are known for building things. I know I've said this before. Engineers, people who become engineers, and we don't have engineering specifically called out in ISBT, but we sort of do in the technology side of things. Engineers are not, in the English language, are not called engineers because they like to run with engines. There is an engineer who actually runs the engine of a train. That's an engineer as well. But a design engineer, in the English language, is based on the root word ingenuity. They're ingenious. They don't have to be geniuses, but they're ingenious. What a great invention. They use their ingenuity, they use their human intellect and genius to design new things. That's what engineers do, because they behave ingenuity-wise. We built this circuit last Monday. It is a resistor. There's R1, okay? And then we had this resistor, R2, and then we had this guy, which we just learned after playing with it on this past Monday, is a light-emitting diode, okay? The light-emitting diode is a device that only turns on when you have enough current and enough flow. It's a diode. It's one of those diodes you have to push first, and then once it gets enough push, it lets the current flow. And we solved this last Monday. Here comes the positive current, I, comes down here, and we learned that this little guy, now that we're magnified, do you see what that guy's made out of? You can see it. Stupid little straws. I keep on showing the straw here, and they go even further. Oh, super secret. Like the CIA. Focus, please. Manual focus. Oh, there he was. Fabulous. Oh, I have the word LED. That's some tagging artist. Look how pretty. It literally is a bent, stupid wire. Okay. This wire in this configuration, they didn't just do that to fit it in there. It's not like your brain or intestines or anything. They really bent it. Okay. They bent it just like when we bend the straw. It adjusts the resistance of the flow of air. That guy, that bent little conductor, depending on how much light hits it, adjusts how much resistance it has. Okay, that's our little guy. So we have a system that's very similar to our bent straw. I'll go back here to autofocus and pull back out. Now you can do it. Here's our circuit. And we looked at this, we sort of walked through this last time. I moved these things around, obviously. This wire now goes over here to keep the electronics lawyers happy. And this guy goes over there to keep the electronics lawyers happy. And if we trace the current with our finger, we know that the current comes down here, goes through this resistor because it's in series. All the current has to go through here. And then it can split. Some of it can go up and through that mess. And some can go down and go through whatever that mess is, and then back out, and then off we go. We said before that the two 1,000 ohm resistors were the same. So if you're talking about a choice, if the current has a choice, half of the current goes this way, the other half goes that way because the resistors were the same size. The resistors here are not the same size. They're much more complex than just a resistor. But we know when we cover this, or we turn out the lights, the resistance of this little bugger goes way high. Okay? It's just how it works. When it doesn't see light, okay, I'm going to draw a nice happy sun. I've got the happiness. There we go. When we have lots of happy sun, the resistance goes up. When it's dark or cloudy, then the resistance goes down. When the
I think you meant to say it the other way.
Oh, I do, because I'm an idiot. Thank you for catching that. This is why we do things in teams. Thank you. It is inverse. In fact, we double checked that it was inverse. When the light is hitting it, the resistance goes down. When it's dark or cloudy, the resistance goes up. That feels better because it's true. It was the opposite direction. The idea is, while the light is hitting this circuit, the current will go through, if it has a choice, again, choice. If it has a choice, will go through the path of least resistance. You've heard that phrase before. It'll go through the wire with the smaller resistance, and it turns out, as long as the sun is shining, the path of the current is this way. Okay, off we go. As soon as it gets dark, or it gets cloudy, or the light hitting this guy starts to the light goes down, then this resistance goes up, and that makes this path stronger. And when the current flows through this light-emitting diode, it too lights up. Okay, you can literally see the current, the electrons, flowing through it, and it glows red. Actually, it glows white, but it's inside a red piece of plastic, is what it is. It goes around. So this entire circuit, as a circuit, reacts to its environment and, I guess, does things sort of intelligently, as opposed to just does exactly what we tell it to do. And of course, this is how we use, if you happen to have a night light at your house, this is how a night light works. This is how those little lawn lights work when it gets dark. During the day, it absorbs light into the photocells and charges up the battery. And then at night, it flows the opposite direction because the resistance is different, and it flows through the little light-emitting diodes, and you have little lawn lights just running around. Okay? We're good? Serial resistance. These two pods this part and this part are in series. The current goes through this first, then, and only after, it goes through whatever this crappy thing is. However, inside this box, these two guys are in parallel. So you can look at the particulars, you can look at the individual details inside this second component, inside of this second system, and notice this is a parallel circuit. So we have a parallel circuit in series with a resistor, and the whole thing just happens to be a nightlight, which is kind of cool. Speaking of getting dark, it got dark all of a sudden. Let me do this. Hi, man. In lab on Monday, we talked about a few other devices, components that interact with their environment. One of them happened to be the thermistor. That's pretty conceptually similar to our photocell. It changes its resistance depending on what temperature it is. And then we talked about this little bugger. Or you can draw it this way. Recall? We called it on
Diode.
a diode. Okay, di usually means two. It just means it has two positions. Again, how does this work? If this is positive and this is negative, that means the current would like to run that way. If this is positive and this is negative, it means the current would like to run that way. So the same thing twice because it's true. When the diode when the real diode is in the circuit the way it's facing on the top one, this is supposed to be like a one-way arrow. It really does let the current flow. The current flows. It's as if someone has closed the switch or closed the drawbridge and let the people or the cars flow. However, if the diode is in backwards, the other direction, nothing happens. This guy turns off. No current. No current. Okay? It's as if, again, you can think of the one-way side's one-way. You can think of this guy as being a drawbridge that's down. This is a drawbridge that's up. Or someone's closed the door. Or somebody's locked the door. It's however you want to think of it. Okay? There are reasons inside electronics to have these diodes to make sure the current only flows in a certain direction. The example I used in lab was your heart valves. I think my heart's over here. Your heart valves open and close, but they only allow blood to flow in one direction. Your circulatory, thank you, system. Your circulatory system has a certain direction that your blood flows. It doesn't go backwards. It just goes in one direction. Okay. There's actually I don't know what it is. Does anybody have that vocabulary word? There's a known condition where humans are born with a counter-circulatory system. Their valves are in backwards. It's not cool. They get operated on very, very quickly. Thank you for Googling it. I probably won't be able to pronounce it, so I hope you can. But hopefully your heart works properly and you have fully functioning valves. Sometimes we have to fix our valves because they're broken. But they allow the blood to open and close to flow in the right direction. Same thing here. What we're going to start today and then finish up on Friday, probably into Monday, is how in the hell does that little diode act like a valve? What? How does it work? Is there like a little tiny traffic cop inside there saying, no, you go this way, you go that way? How does it know that it's facing the wrong way? Does it have a spring? Is it a door? Is it literally a drawbridge? I don't know what's inside of it. For some reason, we have this box, and as long as this is current, current, and this guy is current, as long as the box happens to be in that direction, then the input is current and the output is current. This guy is open. If we do the same thing and the same thing, but this time switch the diode around, nothing This guy is closed. Yay, we get to use our vocabulary words from week 1 and week 2. Our system can be open or closed to the flow of current, completely dependent upon which way it's facing. Okay? Typically, in a real circuit, we don't take our fingers and move it back and forth. That would be a waste of time. Well, if you're getting paid enough, I guess you could be paid as a robot to switch the diode around. But typically, what we're going to do is we're going to move the current back and forth, just like in your heart. And this is going to turn off while it's going the wrong way. So we need a system, we need a component, we need something that will do what this design is. And it turns out that we didn't know about our current diodes until about the 20th century. We just didn't know about this crazy science. And the crazy science we're going to use, thankfully we're on the 3rd floor. It's not to scale. Oh, that's fantastic. I don't know what it is. Anybody know what I draw? Oh my gosh. What'd you say?
No, Sydney looked up the.
Did you find it?
I think it's
Is it pronounceable?
mitral valve prolapse.
Mitral valve prolapse. It allows blood to go the wrong direction?
Yeah.
Not cool. So yeah, that's I guess you could put it like a little, talk about engineer, we put wheels on it and turn it into a steam engine. I was trying to draw that. At least the top of it over there. Yeah, it happens to have another thing down here that we all sort of forget or ignore. This guy on the bottom, maybe that's the tracks or something. Okay. That is a really, really, really broad sketch of the modern Mendeleev. Mendeleev. Yeah, I forget how to say his name. Anyway, it's the periodic table. Okay. Of what? Of the elements. Fantastic. We're on the 3rd floor. Wonderful. Infinite number of points to Gryffindor if you know why we call it a periodic table.
Because they're organized in a certain way based on how they react.
1,000,000 points to Gryffindor. Fantastic. It's a periodic table because different atoms and elements behave similarly as you go across rows and down columns. They have a periodicity to them. There's a start and a stop. You're like, oh, the pattern started again. Look, these guys do the same thing. These guys, when you chuck them in water, they get wet. These things, you chuck them in water, they explode. That's kind of different. It'd be nice to know. Okay, so we put those things on there. Okay, so here's our periodic table of the elements. Right? So if we draw, we sort of have 2 columns to start out with, and then what? 1, 2, 3, 4, 5, 6. 4, 5, 6. And then these guys in the middle are 10, I think. I think there's 10 in the middle there. Okay. And then these guys out here, I think there's 14. Is that right? 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14. There's 14 down there. 2, 6, 5, 14. What's the pattern? Oh, I don't know. This guy is a 1 times 2, and this guy is a 3 times 2, and this guy is a 5 times 2, this guy is a 7 times 2. Oh my gosh, there's patterns everywhere. Oh, it's fantastic. 1, 3, 5, 7. They sort of have a party. What bin do you put? I'm sorry? I say okay, Google or Siri, I'm sorry. 1, 1, 3, 5, 7. What's special about 1, 3, 5, 7?
Prime.
They're primes. What else are they? They're odd. Yeah, so all these lovely things that makes them special. I'm special because I'm a 1. I'm special because I'm a 3 and a 5. There is patterns in nature that sort of repeat, much like our patterns of parallel and serial over here. 1, 2. 1, 2, 3, 4, 5, 6, 7, 8. There's that magic 8. 1, 2, 3, 4, 5, 6, 7, 8. And then after you get bored of doing that, you go 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 8's kind of magical. What other periodicity, what other system do we have inside science or human experience where 8 is special? Spiders, arachnids, octopus, 8. Stop signs are octagons, fantastic. How about a natural system that has 8? I know octopuses are natural. Does anybody play an instrument? Dan, is there anything special about 8 in our Western tradition of music? Octaves, fantastic. What's special about a music octave? Anybody know what's special about a music octave? What about piano? How many keys on a piano? There's Google, right? Is there 88 keys on a foot? So how often does 88 go into, or 8 go into 88? 11. So there's 11 octaves on a piano. They're in octaves. There's a couple octaves there. Octave, 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 octave. What's special about an octave? Oh my God! Please don't tell me he's going to sing. Ready? Do, do, re, mi, fa, sol, la, ti. Do, 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 do. What's special about the bottom and top? It's the same note, but they're octaves different. Okay? Same thing here. They're sort of the same chemical, but they're an octave different. You can tell the difference because they're an octave different, but they sort of repeat. You could play music with this octave, or if you go up an octave, you can play music with that octave. There's periodicity involved in it. Okay? All kinds of neat systems. These guys down here, if you think of a little tiny atom with a nucleus, and then this guy is a list of where the electrons live. You guys have studied the shell model, or the onion orbital model of electrons. Okay. What's special about these octaves? Well, we sort of fill them all up, and then once we get to 8, we go to the next shell, which is an octave higher, and then we go to get an octave higher. These guys down here, they have, well, depending on where you're at, we're talking about the octave, they have 1 or 2 electrons in their outermost shell. These guys have 3, 4, 5, 6, 7, 8 in their outermost shell. So we also have learned in chemistry that when these chemicals combine, they like to have shells that are complete. It's sort of like that music thing again. Having all the notes in a song makes the song complete, as opposed to, I want you to play this song, but you can't play the letter E. You can't play the note E. It would make unless of course it doesn't involve that. So it turns out that we like full octaves. Who likes it? The energy likes full octaves. So when these individual elements combine or react, they would rather lose or get rid of, or here's the word, donate electrons and go back down to their next fullest shell. And the guys on this side, especially if they're a 7, how do you get rid of 7? Alright, just take an 8. Okay? So they usually gain or accept. Okay? Electrons. It's not as simple as there's only 8 notes in an octave. We know there's some black keys as well. These guys here, these are the half steps. These are the black keys in the middle. Okay. But if this condensed into 8, it would look a lot prettier as a system. But if I draw this, like I said, there's a pink line. I should draw with red, right? Do you see that guy over here? It's like this. Those little steps, okay? It's a transition. What's the transition? Trans means across. From here to there. What's... Whoa, fabulous. Everybody on this side of the line, we call them metals. And everybody on this side of the line, really inventive, we call them non-metals. There's the metals and there's the not metals. It'd be nice if they had a nicer name. I'm sure they would appreciate it. There's a hell of a lot more metals than there are non-metals. Maybe that's why the non-metals don't bitch about their name, because there's not many of them. They're just kind of really small. That little corner up there. What's the difference between metals and non-metals in nature? No, good.
Metals conduct electricity.
That's true. That's an attribute. Metals are, at room temperature, normally metals are solid, except for like the crazy ones like mercury and things like that.
Boiling, melting points.
They're all fantastic answers. Here's the official definition. When bonding, metals donate electrons, and when bonding, nonmetals accept electrons. That's the official difference between you go in the nonmetal box and you go in the metal box. Everything else is true. They're shiny, they're heavy, they're conductive, they're non-conductive. All those properties become because of the electrons. Okay. There's a reason why I've started this conversation today, and we're going to finish it on Friday. What are we flowing through our diodes again? What are we flowing through our circuits? Bing, 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 bing. Let's use stuff that donate or accept electrons to carry, electrons. We can use all of those individual elements to move electrons from here to there. When electrons are moving down the line, they're sort of like, here, can you hold this? Sure. Can you pass it along? Sure. Can you hold it? Yeah. Can you pass it along? Sure. That's what makes metals conductive, because they have no problem donating electrons. What about non-metals? When they get an extra electron? Oh, thanks. No, I want you to pass it along. No, I'm good. I'm going to hold on to it. That's why they're insulators. You give them an electron, they say, yeah, thanks. And then we're done. Metals are like, here, can you hold this? Sure. Can you give it to the person next to you? Oh, yeah, no problem. I'll do that. Okay? So metals make fantastic conductors. Non-metals make crappy conductors. We're going to use a combination of both of these guys to build these guys, so we can have them be fantastic conductors sometimes and crappy conductors other times. Now the idea is, when can we tell them to switch? Sure, why not? Now, if we would have thought about this about 1940s, we'd all be billionaires, because it's how every electronic device we've ever used is based on. We just didn't know that before like 1930s, 1940s. We didn't have technology. Okay? Our second hand is frozen in time. No, the big hand is not. Welcome to Closer to Spring Break. Bye.